Thanks for the opportunity to speak. I will also be on the job market this fall looking for postdoc positions. Please consider giving me a job. And aside from quantum Schubert calculus, I've also done some work in classifying co-minuscule Schubert varieties together with Ed Richmond and Mihail Tarigraci, and Ed will talk about this tomorrow. This talk will mostly be based on joint work with Gu, Mihailcha, Sharp, Zhang, and Zhou. And Leonardo has mentioned that Eric Sharp is a physicist at Virginia Tech. Wei Gu and Hao Zhou are his former students, and Hao Zhang is a current student of his. And last night, we posted a paper on the High Energy Physics Archive, which states a presentation for the quantum K-ring of partial flag varieties and gives a physics derivation. We are currently polishing a math paper where we will give a complete proof in the case of incidence varieties FL1 and -1 n, and a conditional proof in the case of full flag varieties. Assuming some conjecture, I will explain more later. All right. Yeah, so if you're interested in polynomials, I invite you to think about what are natural polynomial representatives for these presentations that I'm going to show you. Okay, so what is quantum K-theory and why should we care about it? I made this slide for those of you who want to look at technical definitions, but you don't have to read everything on the slide to understand the rest of my talk. Now I'm going to give you an informal introduction. So in this talk, X will be a K-step partial flag variety over the complex numbers. And from the geometric perspective, classical Schubert calculus studies intersections of subvarieties in X. Kevin was just talking about this at the beginning of his talk. Now, in quantum Schubert calculus, we study curves meeting given subvarieties in X. Oh, okay. Thanks. Yeah, so this is just a cartoon picture. These are my subvarieties, and this is a curve meeting these subvarieties. And for me, a curve is just a map from the projective line to the partial flag variety. Associated to each curve or map is a K-tuple called its degree. And what is the degree? Well, we just pick a general hyperplane, pick general hyperplanes in X, and count the number of pre-images. To be more precise, there are K types of hyperplanes in X because X sits in a product of K Grassmannians. And we can pull back hyperplanes from each of these K factors. Now, if we pick a hyperplane, a general hyperplane of each type, and look at the number of pre-images of this map, we are going to get a K-tuple of non-negative integers. And this is the degree of the map or the curve. In some sense, it measures how twisted the curve is. Now, we are going to be interested in the families of curves of a fixed degree passing through some given subvarieties in general position. So like you can have a family of curves sort of like this. the arithmetic genus of this space of curves is equivalent to a K-theoretic Gromov-Witten invariant. And in the case where there are only finitely many curves passing through these subvarieties, it reduces to the curve count, recovering the cohomological Gromov-Witten invariant. Moreover, we also recover classical Schubert calculus because studying degree 0 curves passing through given subvarieties is the same thing as studying the intersection of those subvarieties. Using these K-theoretic Gromov-Witten invariants, we can deform the tensor product in the Grothendieck ring of algebraic vector bundles on X and get a, by the way, I'm using those angled brackets to denote K-theoretic Gromov-Witten invariants. And this deformed product is denoted by the circle, the same as Leonardo did in his lectures. So with this deformed product, we get an associative and commutative ring, which deforms the usual K ring. And in this process, we introduce the Novikov variables Q. So here, to keep track of the degree of our curves. So this Q is short for the sequence of parameters Q1 through QK. So these are quite analogous to quantum cohomology, but one difference is that in quantum K theory, the structure constants are generally not just one single Gromov-Witten invariant. Rather, they are combinations of many Gromov-Witten invariants. It has to be this way for the ring to be associative. And there is a filtration on the quantum K ring, and the associated graded is gives us quantum cohomology. There is also a T equivariant version, which I will not go too much into. And recall from Leonardo's lectures, we have these Herzebruch lambda y classes, which are K-theoretic analogs of total turn classes. Here, y is a formal variable. The key point about these lambda y classes is that whenever we have a short exact sequence of vector bundles on X, the lambda y class of the bundle in the middle splits as a product of the other two, of the lambda y classes of the other two bundles. And this is very much analogous to what happens for the total turn class. And you can also think of the lambda y class as this is equal sign, as 1 plus y times the first elementary symmetric polynomial in the K-theoretic turn roots of E, and plus y squared times the second elementary polynomial in the K-theoretic turn roots of E, and so on. And if you think in this way, the Whitney relation is just saying that the K-theoretic turn roots of E are the K-theoretic turn roots of E prime and E double prime put together. On the Grassmannian, we have this tautological short exact sequence. And if you want to get a presentation for the cohomology or the K-theory, you just need to consider the Whitney relations given by this short exact sequence. Now, when we go to quantum cohomology or quantum K-theory, these Whitney relations get deformed, so we need to find out what they deform to. Witten did this for quantum cohomology in the 90s, and this is the deformed relation. Recently, Gu, Mihalce, Sharp, and Zhou generalized it to equivariant quantum K-theory. And of course, you can write these as presentations in formal variables, with formal generators and relations, but I'm keeping these bundles to make it clear that the generators come from term classes or wedges of these bundles. So our project is to generalize this to partial flag varieties. So for the k-step partial flag variety, we have k tautological short exact sequences. So we just need to deform each one. We just need to deform the Whitney relation for each one. So these are, so we proved these deformed relations in quantum cohomology, and we give this conjecture in equivariant quantum K theory. So in fact, each step doesn't give you just one relation, but it gives you a set of relations. You should think of this as you're requiring this polynomial in Y to be the zero polynomial. So the coefficients in front of each power of Y should vanish. So for example, if you expand these relations for FL1, 2, 3, then the first step is giving you the first two relations, and the second step is giving you the last three relations. Let me point out that our presentations are different from the Toda presentation by Astashkevich, Sadov, and also Giventhal Kim that Mark was talking about. And it's also different from the recent presentation by Meino, Naito, Sagaki for the equivariant quantum K-ring of the full flags. Because our generators, our relations are both quite different from these, even in the classical case. And by the way, I don't know so we still have the Schubert basis for these rings, but I don't know what are our natural polynomial representatives for Schubert classes. I don't even know this in the classical case. So if you have any insight, I'd be very interested. The closest presentation in the literature to ours is the presentation for the quantum cohomology of Fano quiver flag varieties by Gu and Kalashnikov. So Fano quiver varieties generalize type A flag varieties, and the way they get their presentation is via the so-called abelian non-abelian correspondence. One last point I want to make is that our conjecture is mostly about the claim that these relations hold. Once we know that these relations hold, there is a way to prove that they give a complete set of relations. This has been done for the Grassmannian, and the same method should apply for the partial flags. So yeah, but there are some things. So maybe this slide could be optional. Maybe I don't know. So I'm trying. Okay, maybe it's just one way to look at these, to think about these relations, just to emphasize how Grassmannian-like they are. But since maybe I don't want to keep people here, maybe we can skip this. If you're interested, you can ask me later. So we proved this conjecture completely in the case of incidence varieties. So this is a two-step flag variety. So we get two sets of relations, one for each step. Our proof relies on this formula I proved in my thesis. It says that three-point K-theoretic Gromov-Eaton invariants, where one insertion is the determinant of a tautological subbundle, another insertion is a Schubert class, and the last insertion is arbitrary. This kind of K-theoretic Gromov-Eaton invariants are either 0 or equal to this classical invariant. So here, gamma d of omega is the curve neighborhood Leonardo was talking about. It's always a Schubert variety, and we know exactly which one it is. So, so the right-hand side just happens, it's just a computation in classical K-theory, and it's pretty manageable. And the proof of this formula is geometric. So in my thesis, I eventually used these formulas to get a closed formula for the Schubert structure constants and directly verified that they have positivity. They have signs that alternate with codimension. But here we are using this formula in a different way, where we use these formulas to prove those conjectured relations. The reason we can do this is because, first of all, Schubert classes form a basis. And moreover, in the case of incidence varieties, we can reduce our conjectured relations to some identities that involve only multiplication by these determinants of tautological subbundles. So in fact, this formula is expected to hold for all partial flag varieties. This is a conjecture of my advisor Anders Buch and my postdoc mentor Leonardo Mihalce. And Leonardo stated this conjecture in his lecture as well. But so far, it's not been proved beyond the Grassmannians and the incidence varieties case. If we assume this conjecture, we can also prove our presentation for the full flags. However, it's not going to give us the presentation for general partial flags. That's because we can't always reduce our conjectured relations